Hi everyone, thank you so much for joining us today. We have with us guest speaker Nikhil Vyas. Nikhil is a postdoc at Harvard University hosted by Professor Sham Kakade. Prior to this, he was a graduate student at POC group at MIT, where he was advised by Professor Williams. His current research focuses on deep learning, most recently on optimization. Today, he will be talking about his latest paper on optimization called So. Thank you so much, Nikhil, for your time, and I hand it over to you.
Thanks a lot, Ahmad, for the introduction. So I'm actually going to talk about two papers. So we had a prior work where we were trying to understand shampoo. I'll talk a bit about that, and then I will move on to soap because we use that. I would say, like, if you have any questions, you should just feel free to ask them. I think it's better to focus on the first beginning parts of the thing rather than to sort of try to cover everything. So I think feel free to ask questions if things don't make sense. Okay, great. Let me start. Are things visible to people?
Yeah.
Okay, great. Yeah, so this is like, as I said, these are two papers, and the second one is so the first one is called New Perspective on Shampoo's Preconditioner, and this is a joint work with lots of people at Harvard. So, what's the motivation behind, firstly, behind studying this shampoo optimizer? Well, one reason is that other than shampoo, we really have a lot of optimizers which perform very, very similarly. So this is this plot from this other work that we have that I'm not going to talk about. But what we are doing in this work is that we are comparing a lot of optimizers across different models. So these are all language model training, pre-training tasks, and we are training them for different scales from 150M to 1.2B. And for each optimizer, we are plotting the best performance. So that's the optimal learning rate. So that's always going to be one. For each optimizer, we sort of choose its own optimal learning rate. And we also compare them like how their performance varies across learning rates, so sort of like stability across learning rates. And our overall observation, so yeah, y-axis is the loss, x-axis is multiple of optimal learning rate, where optimal learning rate is defined for each optimizer. So the basic conclusion we had here was that lots of these modern optimizers work very, very similarly. Like Adam, Ada factor, Lion, all of these work very, very similarly, even across learning rate stability and across scales. SGD is pretty bad, but that's maybe expected at this point. But like we don't really have any real improvements over Adam in these optimizers. Maybe one benefit that I will mention of Ada factor and Lion or that they have some slightly less space usage. So that could be useful in certain situations. But performance wise, we don't really get any improvements from all of these optimizers. And one thing to note here is that all of these optimizers are these diagonal preconditions. So what this means is that all of them have some way of determining learning rate separately for each parameter. Like Adam maintains the second moment estimates which determine learning rates for each parameter. Similarly, Ada, Factor, and Lion do something slightly different, but they're all similar and they all are sort of maintain one learning rate per weight per parameter of the network. And what's different about Shampoo is that Shampoo genuinely is the first algorithm that we know of that seems to really conclusively beat Adam across data sets and architectures. And this was proposed in 2018, but the modern version of Shampoo that people use is a bit different than the one that was proposed in the original paper, and we'll come back to this point. Recently, Shampoo also won AlgoPer, which is this challenge of um, various different data sets and architectures and trying to see which optimizer is best. And Shampoo outperformed Adam in this by around like 30% margin. The other thing is also that the fact that something is outperforming Adam means that it says something about the training dynamics of neural networks. And maybe this is like a good lens for us to try to understand just like general sort of science of deep learning kind of properties of neural networks. So maybe I'll just show one plot where sort of this is plot from our paper and we'll come back to lots of these plots. But for now, just this plot comparing Adam to Shampoo, and we've really tuned everything. Like all hyperparameters are tuned here. The things that are fixed is the model size is some 660 million model, 2 million batch size, and we have tokens which are chinchilla sort of optimal tokens, which basically means tokens are 20x of the model size. And what we're doing is that we're comparing these two optimizers, and these are the training curves, and we see that Shampoo is genuinely quite a bit better than Adam. Um, any questions in the sort of the motivation here? Sounds good. So before we dive into like thinking about shampoo, let's first discuss like what is shampoo even trying to do? Like what is the basic class of algorithms, optimizers that we are interested in? And the basic idea behind all of these optimizers, even Adam, shampoo, all of them is preconditioned gradient descent. So what that means is that standard gradient descent looks like, okay, we find the gradient of the loss, we move in that direction or the negative of that direction. What preconditioned gradient descent says is that we instead of moving in the direction of the gradient, we move in the direction of some matrix P inverse times the gradient. And so why would we want to do this? So here's sort of an intuitive picture. So suppose our loss landscape looks like the picture on left. In that case, what happens is that the y-axis has much more gradient than the x-axis. So what happens is that we cannot use a really high learning rate because then y-axis would destabilize. So what we have to do is that we have to use a small learning rate to make sure that y-axis does not destabilize. But this means that the progress in x-axis is very slow, and we sort of take a lot of gradient steps to reach the minima. So the intuition behind preconditioning in general is that we want to start with such loss landscapes and sort of make them isotropic, which basically means that at any point the gradient really points to you in the correct direction. So you can just take a single big step and get close to minima. So that's what all of these optimizers, including Adam, Shampoo, most of these optimizers are trying to do. That they basically try to sort of flatten, sort of make the space isotropic, make it look less elliptical, basically, so that uh, any gradient, our gradients point towards the minima as compared to before. So what's a common precondition? Like what matrix P should we be using here? So there's like sort of common things that were existed even much before neural networks. So the first one is Newton's method. What this does is that it says that the preconditioner matrix P should just be the Hessian of the neural network. Then there's this other method called AdaGrad, which has some slightly different H matrix, which I will not go into for now, and it uses its power minus half. But the only thing that will matter to us for the purposes of this talk is that for both of these methods, H is of this form or close to of this form of the form expectation of gradient transpose. So it's some covariance matrix of some things which either are gradients or are close to gradients. And one thing to note here is that G is a vector, right? So it's a vector of size, number of parameters. And so the common preconditioners that people consider are of this form where you multiply h to the power of some minus p, and h is of the form of the covariance of something like gradients. Right. So sadly, these methods, while they sort of make a lot of sense in theory, they're not really feasible for neural networks. Because as I said, G is of the size parameters, which means H is of the size parameter square. And neural networks have so many parameters that parameter squares is really infeasible. Like you can't store this in any GPU, even like CPU, you will like sort of run out of memory very fast. You don't have enough memory to store the actual H of the neuron, the H matrix in any of these methods. And the other thing is that even for a single layer, suppose you have single layer M cross N, H is still of the size M square N square because G is of size Mn, so H is of size Mn cross Mn, so that's M square N square. This is still pretty infeasible to store in memory. So what do people do in practice? The most common solution to this in practice is just to take the H matrix and just consider its diagonal entries. So for example, that's what Adam does. So Adam is basically AdaGrad. You do two changes to AdaGrad. One, you do this diagonal approximation, and the second one is that you add momentum. But momentum is something that you can sort of add to all optimizers, so I won't get into momentum. So basically for us, for our purposes, Adam is you start with AdaGrad, do a diagonal approximation of the H matrix. That's sort of the most common approximation of these methods. And indeed, Adam, like just a diagonal approximation of these matrices helps us a lot. It is basically uh, the state of the art in the current neural network optimization. Um, so just say, I don't think so. I'm on the PowerPoint, so I won't be able to see if people have questions. So please feel to unmute yourself and ask them if you have them. Okay, great. So what Shampoo does, and This is a general class of approximations. Instead of making a diagonal approximation, Shampoo makes a Kronecker approximation to the H matrix. So specifically for a matrix of dimension m cross n, G, the gradient is an mn dimensional vector. H is of the shape mn cross mn. And so what this means is that if so there are mn rows and mn columns. So rows can be indexed by a 2D tuple I comma j, where I is in m, j is in n, right? Because sort of total number of possible values of I comma j, where I is in m, j is in n, is mn, and that's exactly the size of the number of rows of H. So we're going to be indexing a single row of H by I comma j, and this really corresponds to the ijth weight in the weight matrix. And columns are indexed similarly by I prime comma j prime. So what Kronecker approximations do is instead of approximating H by a diagonal matrix, they say that we will approximate H, specifically the I prime j prime entry, by a product of I prime R j j prime. So you're sort of the matrix has like ij as the rows, I prime j prime as the columns. What we are going to do is that we are going to split the matrix into an I prime component and a j j prime component. That's sort of what they do. But maybe here's a better intuitive way to think about Kronecker approximations. So note that sorry, I'll just go back a second. Note that what we want to do is that we want to take a matrix and multiply it to the gradients. It turns out that if your matrix is of a Kronecker product form, then multiplying the matrix to the gradient is the same as firstly considering so remember the gradient is the gradient of a linear layer. So it's an mn dimensional gradient. You can also think of it as an m cross n matrix. So Kronecker products are products so that when you multiply H to G, that's the same as left and right multiplying these L and R matrices to the G matrix. So maybe this is sort of maybe the most complicated part of these things, that multiplying by Kronecker products to vector G. So if H is of the form L cross R, this is how Kronecker products are indicated. So multiplying L cross R to the vector G is the same as left and right multiplying L and R to the matrix G, right? Like up to the entries, up to making vectors into matrices. So this is maybe the most non-trivial part. But I hope this gives some intuition as to why Kronecker products make sense. They are basically approaches to have these structured preconditioners. Instead of having like a full Mn cross Mn matrix, we consider preconditioners which are equivalent to left and right multiplying the gradient matrix by two matrices. Uh, is there a question? Or okay. Okay. Yeah. And the interesting thing here is that H matrix was of size m square cross n square, n square, sorry, m square times n square, which is infeasible as we have discussed. This is just of size m square plus n square because L is of size m square, I prime both are in M. So L is a matrix of size m square, R is a matrix of size n square. So this is really a feasible thing to store as compared to m square n square. Okay. So okay, this is like general Kronecker approximations. Now we can ask what are the specific L and R that Shampoo chooses. I should just mention that this form of approximation, instead of diagonal approximations, is used by K-fact, Shampoo, and also ADA factor. So if people have heard of ADA factor is actually uses a preconditioner, which is both a diagonal preconditioner as well as a Kronecker product preconditioner. Yeah. But now we should let's go to what specific L and R does Shampoo use. So what Shampoo uses is specifically it says that we will approximate this H matrix, which is expectation of gradient transpose. So this is like vector gradients again. As so the L matrix is expectation of matrix gradient transpose to the power of half, and R is similarly expectation of matrix gradient transpose G again matrix gradient to the power of half to the power of half. And as a note, as a reminder, capital G is just the vector G reshuffled into a matrix. And because we are sort of going to follow ADA grad for this paper, the direction of our movement is going to be h to the power of minus half. So you already had halves here and we have the new half here. So what we get is that the direction of movement becomes, you get these minus 1 by 4s. So this is what the original Shampoo paper proposes as the direction of movement for the weight matrix. Any questions in this description?
Question. Do you have a different slide? Do you have an estimation of the error between the approximation and the real one?
Sorry, I don't think I was able to fully catch it. I don't know if there's something wrong on my side, or maybe it would be helpful to just type the question. If you want. Okay.
Can I ask a question? Can you hear me?
Yeah. Go ahead.
So, why does this approximation by Shampoo make sense on the high level? Like, why is GG
Great.
transpose?
Yeah, no, it doesn't. A priori, it doesn't make sense, right? I'm just trying to say this is what they do, and I'll come to why this makes sense or doesn't make sense to sort of like that question in a bit. But I agree, like a priori, this doesn't like is not obvious. So sorry if I'm pronouncing your name wrong. And here is the question that like how good is Kronecker approximations in general, or how good is the Shampoo's approximation?
So Anier is asking, do you have anything about
Shampoo
approximation for Shampoo?
Yeah, I read. Yeah, I'm on the thing. Okay. Thanks. Yeah, so for specifically for Shampoo, no, we won't say anything. What we'll say is actually like, let me come to it. I think I will answer your question in a bit. Yeah. Great. So what we will propose, and I hope this answers some of these questions, is that this is actually not the correct direction to be moving in. What we will conclude is that the right approximation is actually sort of the square of this, which at least in direction, which is that you don't have these powers of half. But you will note that if you remove the powers of half, right? Suppose ignore the trace part for now. If you just ignore the powers of half, this approximation is not even like dimensionally consistent, right? Like there's like 2 GG, it's like sort of square in the dimension of G, but here you have 4 Gs. So if we just remove powers of half, this would not make sense. But what we additionally have is this trace term in the denominator. So this makes it dimensionally consistent. So we'll argue that this is the right approximation. And hence we will argue that actually h to the power of minus half, then h to the power of minus half, instead of getting minus 1 by 4s, we get minus 1 by 2s, at least directionally. So I'm going to ignore the trace as the sort of as a scalar term, but this is the right direction to be moving in instead of this direction. Okay. And I'll come back to the question of approximation in a bit. But now, let me just see if there's any more questions. Okay. So what we will in fact show is that this approximation that we are doing, which is like instead of power half, power ones, this approximation is actually close to the optimal Kronecker approximation of this matrix. So I won't directly address the question of like how good is the optimal Kronecker approximation. I mean, we'll see empirical plots, but not theoretically. But what we will address is that this thing is as close to is like basically the optimal Kronecker approximation. So you can't do better approximation of this matrix than this object, which is the square of the Shampoo object, unless you go beyond the Kronecker product form. Okay, great. But let me just say an interesting fact, which is, which sort of like is about like how good like empirical people are. So somehow empirical people have already noted this without sort of like thinking about this from first principles. They just tried to sweep this power, and they'd already claimed that Shampoo square works better in practice. So this 2018 paper by Rohan Anil and others, which sort of tried to make Shampoo practical, already noted that Shampoo square works better. And recently there's this implementation of distributed Shampoo by people at Meta. And they also found that Shampoo square works much better. They find either use square or 1.82, but basically things which look more like 2 than 1. And sadly, I don't have great plots here, but I do have these 1 dB plots. And so here what we are doing is that we are comparing exponent power 1 by 4 to power 1 by half. And indeed, power 1 by half works much better. But really, people had already noted this before that this Shampoo square works much better. But let's come back to the question of like what happens here, right? So this is the approximation. This is Shampoo square, which is what we are proposing. Now let's see empirical results as to like how well do these two approximations work. Okay. So these are two approximations. One of them is on the CFAR 5M dataset. The other one is on the ImageNet dataset. The x-axis is the training step. So we are measuring approximation and multiple points in the training, sort of the training dynamics. And what we observe is that optimal Kronecker approximation, which is sort of the best thing you could do to approximate the H matrix, is, maybe like, just like sort of an average value seems to be around 0.8 after like at least halfway down after the training or something. And Shampoo square is basically on top of optimal Kronecker approximation. Like it's very, very close. And Shampoo is much worse, right? So there really is a sense that this is the right approximation of the H matrix, and Shampoo is sort of significantly worse than this. And the other thing to maybe that is interesting is to think about like how much do these Kronecker approximations even capture H, and they seem to capture around 80% of the so the cosine similarity is around 0.8 between the real H and the approximated H. And this is quite impressive in some senses because the real H is of size m square n square, while these approximations are of just size just m square plus n square. So for like real matrices of size like 1000 cross 1000, this is like a million times smaller approximation. But it still is capturing 80% of the, it's still sort of like 0.8 cosine similarity. So I think this is like quite impressive that this captures so much of the approximation. Okay. Maybe I'll ask the people who are sort of, people had questions about the approximation. Does this make sense? We'll come back to why Shampoo square is the right thing to do. But I'm just saying, does this give, oh, maybe there are a lot of questions. Let me just see this. Right. Yeah. I don't understand why they got 1.82, but I think this is just some sweeping. But the point I was trying to make is that it's pretty close to 2. Right. That's a good point. Why cosine similarity and not some norm? I think this is just because I think we just started out with this. This is like pretty somewhat easier to code up than the norm thing. I think that's about it. Like you could have done the trace thing. I think we tried this in few of the setups, and this does work out. This is just, yeah, this was sort of easy. Yeah, I'm not sure how they arrived at 1.82 either, but yeah. Okay, great. Any further questions on the experimental setup? Okay, sounds good. Okay, now I'll have like one slide. I have more slides, but I think maybe this is sufficient to give, and people can sort of like, people can ask questions and I can tell more, but on like why the Shampoo square makes sense. So remember, like let's remind ourselves what the Kronecker approximation looked like. This is what a Kronecker factor approximation looks like, which is that if you have I prime, j prime indexing the rows and columns, you put the I prime terms together, j prime terms together. And so one thing to note here is that Kronecker products, in some senses, really look very similar to like outer products. Why is that? So outer product of two vectors has this property that for every pair of entries in the two vectors, you get an entry of the final produced matrix. And I want to sort of claim that this is also true for Kronecker products. So for every entry of L, which is I prime, for every entry of R, j prime, there is an entry in H, which is just the product of these two things. So this is exactly what outer products do. But somehow now things are structured as a matrix and sort of there's something non-trivial going on there. But really this looks very similar to outer products. And in fact, you can formalize this connection to outer products. What you can say is that, okay, let's take our matrix H, which is of size mn cross mn. And let's construct this different matrix, which is instead of size m square cross n square. And what we'll do is that we'll have this restructure operation which does this. So we'll say the restructure of H, the I prime, j prime entry of this restructure H matrix is the I prime, j prime entry of H. So one way, if people are familiar with tensors, is that in some sense you should think of H as a 4-dimensional tensor, with the axis being m and mn. So you have these 4 dimensions. H is one way of flattening this 4-dimensional tensor, making it mn cross mn. And restructure of H is another way of flattening this tensor, which is m square cross n square. But what's important to us for the connection to outer products is that if H is the Kronecker product of L and R, then restructure of H is actually just the outer product of vectorization of L. So you take the L matrix, flatten it into a vector. So it's just vector L, vector R transpose. So like what I'm trying to argue here is that Kronecker products are just the same as outer products once you shuffle the entries around. And this is like sort of very important to us because now we can just use this basic lemma to say the fact that if L cross R is the optimal Kronecker approximation of H, then vector L, vector R transpose is the optimal rank 1 approximation of this restructure matrix. Right? And this is not something that we did. This is from this 1992 paper. If you go to Wikipedia page of Kronecker approximations, you find that people have, so they cite this paper and they say that this is the way to find optimal Kronecker approximation of H matrices. But this is very nice for us because, we wanted to think about optimal Kronecker approximations. And what we are saying now is that, okay, optimal Kronecker approximations are the same as rank 1 approximations of some slightly modified matrix. And the nice thing is that rank 1 approximation has an easy algorithm, right? Like power iteration is an easy algorithm to solve for rank 1 approximation of any given matrix. Okay, sorry, give me 1 second. Let me write this thing. Yeah. Okay, good. Yeah, so maybe I will not say much here, but I'll just say that now you can do some power iteration in the restructure world and then try to come back to the original world. And what you get is that one round of power iteration is exactly equivalent to Shampoo square. One round of power iterations when you initialize things with identity. So I won't go into the details, but I guess what I want to convey is that rank 1 approximation is easily solvable by power iteration. You can write down the equations for power iteration and then convert them back to equations for sort of in the matrix world, the other non-restructured world. And that exactly gives you Shampoo square after one round. But maybe I'll skip this unless people have any specific questions. But that's sort of maybe the intuition behind how the proof goes through. Oh, wait, am I not screen sharing? Sorry. About that. Okay, yeah, sorry, yeah, this is better. Yeah. So yeah, sorry, this is what I somehow the screen sharing went away, but the idea here is simply that, yeah, you can do one round of power iteration that sort of explicitly you can write down equations for that and convert them back to this other non-restructured world. Yeah, okay, great. So we have some other results in the paper. We explain like why one step of power iteration suffices. It's not sort of an obvious argument that it's rank 1 or something. It has something to do with how we initialize things to be identity. And someone asked this already, like why focus on cosine similarity? In the paper, we also derive the magnitude. All of these things go through. And the other thing is that for the Hessian, there are some other things like effect of batch size, sample labels versus real labels. We study things like that also in the paper. And as I also mentioned in practice, people already sweep over the exponent. So this doesn't directly help us in improving the optimizer. But now we sort of like, okay, we had this results and we sort of thought that, okay, given these results, let's try to improve Shampoo. But the question is that if we think that Shampoo is already optimal, Kronecker approximation is very close to that, then how could you improve this further, right? Like that's the question. So there are still, so the point here, the reason we could still improve Shampoo is because there are still some drawbacks to Shampoo. Specifically, the first one is that you have like a lot of hyperparameters in Shampoo. Like this power update, people try power 4, power 2, and so on and so forth. There is an epsilon in regularization. In practice, people do this thing which I did not talk about, which is called grafting, and you need hyperparameters for that too. So there's really a lot of hyperparameters in Shampoo. That's one thing that you could try to improve. The other thing is that, we saw these powers of -12 and -1/4s. Those things are actually computationally expensive, or at least they are expensive on GPUs. So what people do in practice is that they only compute them once in a while. So you have this hyperparameter called preconditioning frequency, and only let's say preconditioning frequency is 10, then only every 10 steps would we actually compute the power -12. But what happens due to this is that as preconditioning frequency increases, the overhead reduces, but the performance becomes worse. So what we are doing here is that we are comparing shampoo to Adam, and we are changing the preconditioning frequency on the x-axis. And as preconditioning frequency increases, the performance of shampoo becomes worse. It's still better than Adam, but at this point, it's like a very small difference. So you really want, we somehow want an optimizer which has these two properties. First, it doesn't have that many hyperparameters, is easier to tune. And secondly, maybe performs better with larger preconditioning frequency. So this is sort of the now I'll maybe stop here and I'll sort of move on to the soap work, but I want to see if people have any questions till this point. Okay, sounds good. So the other thing, okay, so now we have this like sort of like a nicer version of shampoo basically, which is like maybe in some senses we have derived this. So in this ideal version of shampoo that we derived, this is what the update equation looks like. We still have the trace because this was the scalar constant, but now you have powers of minus half instead of power minus 1/4, and this is what the update looks like. What you can show, and I will not go into the detail, is that this is in fact equivalent to running this ADA factor optimizer in the eigenbasis of shampoo. Specifically by eigenbasis of shampoo, what I mean is that you find the eigenvectors of this matrix and of this matrix, so the L and R matrices, project G into that in their basis, and then just run ADA factor in that basis. It turns out that these two optimizers are actually equivalent. But one thing you'll note is that in this ideal shampoo and in this ADA factor version of shampoo, we have sort of reduced a lot of hyperparameters. There is nothing like grafting. I didn't explain how grafting works, but it sort of requires a bunch of hyperparameters. We don't have any grafting. It's sort of this like reasonably simple equation. But instead of running ADA factor, which is what this is equivalent to, we can just run Adam. Adam usually performs slightly better, but more importantly, like people have just more empirical experience with Adam, so it's kind of nice to have Adam as it is. And what this means is that we now have an optimizer which is basically just Adam. So there's only one extra hyperparameter over Adam, which is that we have this frequency still, which is like how frequently do we update the eigenbase. But except that we'll just run Adam in this rotated world. Finally, what's the other benefit was this preconditioning frequency. Like as preconditioning frequency increases, the performance of shampoo was becoming worse. What we can now do is that because we have decoupled the eigenbasis and running Adam in the eigenbasis, is that we can run Adam every step instead of running Adam every 10 steps or something. But the eigenbasis itself can be updated every 10 steps. So now the benefit is that specifically we get more adaptivity due to being able to run Adam every step. While the original shampoo was coupling both of these things, both the sort of the eigenvectors and the eigenvalues were being updated every 10 steps. Adam is sort of acting as eigenvalues here, and we can update that much more frequently at every step basically. And eigenvectors themselves can be updated much more slower. So maybe, and as I mentioned, there's no other hyperparameters over Adam apart from preconditioned frequency. Yeah. So maybe I'll just like try to walk through the pseudocode and this simplified pseudocode to help around, sort of like give some intuition of what's going on. So we get some gradient of a linear layer M cross N. We have some eigenvectors, which we'll come back to in a second, how they are derived. We project G using these two eigenvectors. So eigenvectors of L and eigenvectors of R. So we go to a rotated world. We basically run Adam in this rotated world. Once we have the Adam update in the rotated world, we just come back to the original world by just rotating things back using the same eigenvector. And then we take a step in this direction. So basically, the algorithm is pretty simple. You first get the gradient, move the gradient to the rotated world, run Adam there, and then come back. Now the question is like, how do we update the rotated world? And this is sort of like what Shampoo does. You have these L and R matrices, which are just accumulations of G transpose G. And the eigenvectors are just eigenvectors of these two matrices, the L and R matrices. These are the same as Shampoo. But the thing is that these eigenvectors are only being updated every, let's say, frequency many steps. So every 10 steps, while Adam is being updated at every step. This gives us more adaptivity, and this sort of leads to performance benefits, which we will see. But does the pseudocode intuitively make sense? I'm happy to go over some more details if it doesn't. Yeah, sounds good.
So what's the peak frequency here?
Yeah, so we'll come to in the plots that we will do, the frequency will be 10, but we'll also change the preconditioning frequency and compare things. Yeah, we'll change the current plots. So yeah, there's a question which is that do you have a comparison to things like Lion? So I'll say for Lion, as I showed in the first slide, Lion really seems to perform as well as Adam, at least in these language model pre-training tasks, which is something that other people have also observed. Yeah. Great. So now let's compare these three optimizers, specifically Adam, Shampoo, and Soap. Oh, wait, sorry. This. Right. So let's compare, like, okay, let me just explain the plots. The first two plots are the 660M language model. There's 2 million batch size, and the frequency is fixed to be 10. And the first plot specifically is training steps. The second one is wall clock time. We now have like improved versions of wall clock time because we have reduced a bunch of overheads. But okay, these are like the plots. I think they sort of convey the main points. And what we see, we'll get to the third plot in a bit. What we see is that Adam performs the worst. Shampoo, which is the green line, outperforms Adam at frequency 10. But Soap outperforms both of them basically. And so what we have here is that we have a SOAP run which is better in performance. We also have a shorter learning rate schedule SOAP run to be able to better compare to Adam, like how much performance benefits are there. So with Adam, we usually get around like maybe like 40% performance benefits or something like that. This depends a bit on the setup, but maybe that's a good number to keep in mind. With Shampoo, I would say I think the numbers look something like 20% or something like that. But this also depends a bit on a bunch of things. And also we don't have as many hyperparameters as Shampoo. And so this is training steps. This is wall clock time. And finally, in both of these plots, we are fixing the frequency to be 10. Now we can compare, we can vary the preconditioning frequency and see the effects. So this time this is a 360M language model, the same batch size. We are training always for chinchilla optimal tokens. And what we see is that at frequency 1, Soap and Shampoo are very, very close. And this is expected, right? Because if you tune everything, you still have to tune more things for Shampoo just because it has more hyperparameters. But once you tune things, Soap and Shampoo are pretty close. And this is expected because the benefit of Soap beyond the hyperparameter point is that it has more adaptivity as preconditioning frequency increases. So at one frequency, there's not much of a benefit. But as frequency tends to 100, the gap is pretty wide between Soap and Shampoo. So at sort of large frequencies, Shampoo is much worse than Soap. And we have some more improvements here, but these are a bit older plots. But yeah, does that answer the question? Or any other questions on these plots? Okay. Sounds good. There's some maybe other interesting things. Like one thing that people are interested in are being able to train with much larger batch sizes because that sort of reduces the serial runtime of these language model training, which is quite large. So we sort of have these comparison of how Adam compares to. Oh, I should do this maybe. Yeah, sorry. We'll get to this plot. We have some comparison of how Adam compares to Soap as batch size increases. So Adam starts to basically flatten out much earlier than Soap does. So Soap is already better at smaller batch sizes, but the gap increases at larger batch sizes. And this is generally true for any of these methods which try stronger preconditionings beyond Adam, that their benefits are larger at larger batch sizes. And maybe I won't go over too much about this plot, but in the paper, we have some other versions, like instead of Adam, you can use Ada factor. Instead of running Soap on both sides, you can just run this on one side. You can combine one side with Ada factor. So a bunch of things to reduce like space overhead and things like that. And this really depends on the setup. Like I think suppose you have something like mixture of experts or something, then you really may want to run, like a one-sided version of Soap because two-sided would be too much, would have too much cost. So there's a bunch of things that kind which depend on the exact architecture and so on, but we have a bunch of variations which may be more useful in certain settings, depending on what the bottlenecks are, depending on the training regime. Yeah. But yeah, and all of them are like either as good as like you can sort of reduce the overhead significantly of space or anything like that. And still they are able to basically match Shampoo at least and sometimes outperform it. Okay, I think these are the more things. I think there are some other directions, which is that, when we showed the optimality of shampoo, this was in Frobenius norm. It's unclear if this is the right notion of optimality. It's sort of certainly a starting point, and we are thinking about this question. And like, what are sort of other notions in which you can think about approximating as a Kronecker approximation? The second question, which is more open-ended, is that currently we are doing layer-wise approximations, and for each layer, there's a Kronecker product approximation. You could ask, can we do something more interesting here, basically? And finally, there's the question of, can we reduce the overhead further? So there's this new optimizer that people on Twitter, like Keller Jordan, Jeremy Bernstein, are exploring, which is called Muon, which sort of has no overhead, and it's sort of shampoo-like. In our comparison, soap seems slightly better, but in certain settings, I think Muon could be like very useful because it has nearly zero overhead, basically has zero overhead over SGD with momentum. So yeah, I'll maybe put the main plots here, and yeah, thanks for listening to my talk. I'm happy to take any questions.